Hello, you're welcome to this lesson. In this video, you're going to solve this differential equation that I have here on the screen. We are still on exact differential equation. Okay, so we're going to use the same steps that we followed to solve the question in my previous video to solve this one also. If you haven't watched that video, you can check in the description. You'll see a link to that video. Please watch it so that you can understand the whole process. Okay, so just like the previous example, the first thing we must do is to identify our m of xy and n of what xy. Okay, and to do that, we know that we have to rewrite the equation in such a way that we can get a zero on the right hand side, just like the general form. So for this reason, we're going to have 2xy squared plus 4. Okay, then I'll take the terms on the right hand side to the left hand side. So you're going to have minus 2 multiplying 3 minus x squared y multiplying y prime, which I write as dy dx. Okay, and this will be equal to 0. Okay, so from here, you know that in the general form, the sign that is separating the two functions, which is m of xy and n of xy, must be a plus. Okay, so let me just write the general form down. So the general form is going to be m of xy plus n of xy, okay, dy dx. Okay, so this is the general form. So that's why I wrote the differential equation in this form. But for the general form, you see that the m of xy and n of xy are separated by a plus. But over here, we have a minus here, which means that I'll have to change the minus to a plus. So let's look at what you're going to do. So you're going to have 2xy squared plus 4. Okay, and because I want a plus there, I'll write plus 2, and then since I've changed the sign, we are going to have x squared y minus 3 to be in the bracket. Okay, because I changed the minus in front of the 2 to be a plus, the signs for the terms inside are also going to change. Then I'll have my dy dx here, and then this will be equal to 0. Okay, so from here we can find our m of what xy, then that will be equal to 2x y squared plus 4. Okay, and then the n of xy will be equal to 2 multiplying x squared y minus 3. So we can actually expand this bracket. This will give us 2x squared y minus 6. Okay, so now that we have m of xy and n of xy, we can test for exactness to know whether our differential equation is exact before we go ahead and then find the solution. So to test whether it is exact, I will differentiate m of xy with respect to y. So we are going to have my okay, to be equal to, we are finding the partial derivative, okay, with respect to y. So we are going to have 4xy, okay, and then for the 4 here, it becomes 0 because we don't have any y variable attached to it. So we are going to differentiate n of xy also with respect to x. So when you do that, we are going to get 4xy again. So you will see that these two, the partial derivative of m of xy with respect to y is the same as the partial derivative of n of xy with respect to what x. Okay, so from here we can go ahead and find a solution to the differential equation. So to do this, you have to integrate either m of xy or n of xy, depending on the one that will be easy for us. So in this case, I will choose m of xy. Okay, you can also try it with n of xy. They are all easy. So we are going to have our phi of xy to be equal to the integral of m of xy with respect to what x. Okay, so I'm going to have this to be integral of 2x 2xy squared plus 4 dx. Okay, so now let's do this integration. So when you do this, you're going to have 2x squared y squared over 2 plus 4x. And then instead of the constant of integration, you're going to bring a function of the remaining variable y. So we are going to have h of y. So when we simplify this, you're going to have x squared y squared plus 4x plus h of y. So this is part of the solution. It is not complete because we have an unknown function h of y there. So to get a complete solution, we will have to find the value of what? H of y. So let's look at how you are going to do this. So to find h of y, we'll have to find the partial derivative of phi of xy with respect to y. Okay, so when you do this, you're going to have 2x squared y plus, so for this time there's no y variable there, so it becomes 0. So you're going to have plus h prime of what? Y. So from here, you're going to compare this to the other function, which is n of xy. Okay, so let's equate this to n of xy, which is 2x squared y minus 6. Okay, so from here, you can see that 2x squared is here, 2x squared is here. So therefore, h prime of y will be equal to minus 6. But we need h of y, so you have to integrate this with respect to y. Okay, I'm going to integrate this with respect to y. Okay, minus 6 y. Okay, so let's do this. So when I do this on the left hand side, we're going to have h of y, and on the right hand side, we're going to have minus 6 y. Okay, so you can put this back into the phi of xy. So then you're going to get phi of xy to be equal to x squared y squared plus 4x plus h of y, which is now minus 6y. Then we can bring the constant of integration also. Let's not forget plus c, so plus c here. So this becomes our general solution. But you have been given some initial conditions, so you can find the value of c so that you can get our particular solution. So to find the value of c, I will write the implicit solution, which will be x squared y squared plus 4x minus 6y equals c. Okay, so when I have it in this form, I can put in the boundary conditions or the initial conditions to find the value of what c. Okay, so let's look at that. We're going to have minus 1 squared multiplying 8 squared plus 4 multiplying minus 1 minus 6 multiplying 8 to be equal to c. When you simplify this, you get c to be equal to 4. So you can now bring it back to the phi of x. Okay, so let's look at that. So when I do that, instead of c here, I'll clean it and then bring the 12 there. So you're going to have x squared y squared plus 4x minus 6y plus 12. So this becomes our particular solution. Thank you very much for watching this video.